Hello, my name is Riko Morita. I'm a graduate student at Chuo University. It is a great honor to be able to speak to you. Today, I'd like to talk about drifting behavior focused on the initial positions. This is today's contents. Now, I'd like to talk about the introduction first. The Tohoku-oki earthquake, which occurred on March 11, 2011, showed a tremor of magnitude 9, one of the largest in Japan. The tsunami triggered by the earthquake resulted in tremendous flooding and debris from the collapse of houses and secondary damage from drifting vehicles, containers, and ships. However, the tsunami's washed away is not limited to structures such as containers and ships, but includes many people, leading to an increase in missing people and death. From the viewpoint of facility protection and life-saving, it is essential to predict drifting objects, behavior, and range when a tsunami strikes. Next, this is a previous study on drifting behavior. Regarding the reproducibility of the variation in drifting behavior, Goto et al. Established a calculation method for defining the diffusion coefficient in 1982 and demonstrated its validity for the local calculation. Shigihara et al. Made it possible to reproduce the unique spread of drifting objects by changing the value of the diffusion coefficient. However, due to insufficient variability reproduction, many drifting experiments have been conducted. From a field survey, Naito et al. Found that the drifting behavior was within a range of 22.5 degrees in downward direction. Nistor et al. Proposed the spread angle of drift objects based on the number of them. Stoll et al. Used the standard deviation to show the formula for assessing the spread angle of drifting objects. The prediction of human behavior and landing points after being swept away by the tsunami is essential to reduce human damage. Also, drift analysis is not systematized and there are many unexplained parts. Therefore, many experiments and considerations are required. So, this is the purpose of this study. First, perform hydraulic experiments to examine angles and variations due to changes in the initial position. It is necessary to perform numerical calculation considering the variation and create a drifting distribution. As the first step, we will examine the reproducibility without considering the variation. Finally, adapt the current numerical model to local area. These are the study flow of this research. Next is about experimental study. This is the scale of the hydraulic experiment. The experimental water tank was 8.78 meter long, 4 meter wide, and 58.5 centimeter high. The width was set to 2 meter by using a partition plate. These are the experimental conditions for each case. I changed the arrangement of the drifting objects and realized 7 cases. 4.5 centimeter solitary wave was created as wave-forming condition. The drifting model is 4 centimeter long and wide and 2 centimeter high and has a specific gravity of 0.56. This is the result of experimental case E01. In this case, 4 drifting objects were placed 40 cm from the short line and the equal intervals also 40 cm. You can see from the video that the behavior of the 4 drifting objects is different. The figure below shows all the behaviors of the result of 30 experiments. It can be seen that there is a large variation in both the flow direction and the direction perpendicular to the flow direction. The movement distance in the flow direction is summarized every 50 cm in the flow distance and the movement distance perpendicular to the flow direction. That is the movement distance in the y direction from the initial position. Since there was a negative bias due to the topography slope, we created a probability distribution using the probability density function with the average set to 0. The normal distribution can be seen at all points and that the ridge becomes smoother as the distance traveled increases. The horizontal axis is the movement distance in the flow direction, and the vertical axis is the standard deviation of the variation in the direction perpendicular to the flow direction. The yellow line is the spread angle of drifting objects shown by ASCE. The spread of these experiments was smaller than that. In all cases, it can be seen that standard deviation became high when longitudinal displacement was increased. The 6 cases other than E06 tended to spread more slowly, and the standard deviation values up to a travel distance of 1.5 meter were almost the same. This shows that the degree of variation in drifting behavior does not change even when the initial position changes. From this, it is considered that the drifting area of objects can be evaluated from parameter of the wave height and the movement distance at the short line position. On the other hand, when the drifting objects are adjacent to each other as in E06, the spread becomes large, which is considered because the objects interfere with each other and the flow condition changes. This is an evaluation formula for the spread drifting objects proposed by Stahl et al. Displacement is the depth of inundation, the number of drifting objects, and the distance traveled in the downward direction. To examine the effect of the number of drifting objects, the spread of experimental cases E01 and E06 was evaluated by this formula. As a result, the empirical relation proposed by Stahl et al. Overestimated the standard deviation. Therefore, a new evaluation formula was studied using the condition of this experiment. When the maximum value of the variation was taken using this experiment's results, the formula at the lower left was obtained. The problem of this evaluation formula is the effect of experimental scale. It is necessary to consider the adaptability when the shape and the size of the drifting objects are changed, and consider the influence of the similarity law. Therefore, further experiments with different conditions are required. Next, I will explain the numerical calculation method. StockML, which is software developed by Tomita, was used for the fluid calculation. The basic equations of this software are the continuity equation and the Navier-Stokes equation. Next, the StockDM, which Honda developed, is the model to see tsunami debris drifting behavior. This model's analysis method calculates the force acting on the drift object from the drag and inertial forces. By connecting these, the force received from the fluid is calculated. By the way, this calculation passes the water level and fluid velocity data from StockML, but StockDM doesn't affect the fluid unless the road is completely prevented. The calculation target has shown in the figure. The cell size has set to 1 cm in the x and y directions, and the experimental data measured by WG1 was used as the incident wave. From the above figure, it can be seen from the experimental results that there are variations in the direction perpendicular to the flow direction with each trial. The figure below shows the frequency distribution of the movement distance in the experiment's flow direction every 40 cm. The range of variation was large, and the calculation result was overestimated by 18% from the experimental value. On the other hand, it goes straight without shaking in the direction perpendicular to the numerical calculation flow direction. This is considered because the flow velocity in the y direction is not incorporated in the current numerical model. Next is about applicability to local area. We applied this to the local calculation. This calculation targeted 5 locations in Iwate and the Miyagi Prefecture, Miyako, Yamada, Kamaishi, Minami Sanriku, and Natori. The calculation area are shown in the table. The time step is 0.05 seconds, and the calculation time is 7,200 seconds. The drifting object imitated a human being with a length of 1.6 meter, a width of 0.4 meter, a height of 0.4 meter, and a specific gravity of 1. We assume that people at the place where inundation depth is higher than 1 meter was washed away and examine where they have washed away. First, we calculate the inundation range, and drifts were placed randomly in the area where it was higher than 1 meter. These are videos of calculation result for Yamada and Natori. In Yamada, it can be divided into those that move significantly and those that do not. Those that move a lot were pulled offshore by the pulling waves and then drifted in the bay. On the other hand, in Natori, all were washed away on the land and none were drawn offshore. It is conceivable to be due to the difference in topography. In Yamada, where the coast shape is complicated, it is drifted offshore by the first wave and then drifted modal in the bay by the reflected wave. In the numerical calculation, we calculate the percentage of people washed away by tsunami. The actual percentage of missing person is used for comparison. 5 cities below the red straight line has real coast, and the calculated values were higher than the actual values. However, in Natori, all the drifting objects were washed away in the landward direction. However, some people were actually washed offshore. This may be due to the effect of structures and debris. It is necessary to examine in detail how those who failed to evacuate were washed away. It was also found that the proportion of missing people changes greatly depending on the shape of the bay and the topography. Due to the greater fluid force acting than in reality, and the exaggerated drifting behavior, the calculation result for missing washed away became excessive in areas with clear coast. On the other hand, in the plains, it was swept to the land side more than it was, and it was significantly underestimated because it was not affected by the pulling waves. Therefore, it is necessary to improve the moving distance in the flow direction. Besides, since the variation in the direction perpendicular to the flow direction cannot be reproduced, it is necessary to incorporate the spread of the normal distribution as obtained in this study. The varies greatly depending on the drifting object's shape and size, and it's not clear, so further experiments are required. This is our conclusion. The variation in the perpendicular direction from the flow direction was less than the variation estimated using existing evaluation formula. Construction of numerical model that takes into account the spread of the normal distribution obtained in the experiment in the future task. However, variability is thought to depend on the shape of the drifting object and requires detailed research. As for the moving distance in the flow direction, the calculated result in the experimental value were almost identical. However, the evaluation of variability is insufficient. It was able to reproduce the human drifting behavior qualitatively by local calculation. It will be necessary to incorporate the reproduction of the variation obtained in these experiments. Thank you for your attention.